Okay, in this video, we're going to look at how to use calculus to analyze functions and find their characteristic features. In particular, we're going to be looking at functions defined by fourth degree polynomials. In our two previous videos in this series, we have looked at functions defined by cubics. All right, so what we will do is find the stationary points, and then we will determine their nature. We'll find the y-intercept. These two will be enough to enable us to make a sketch. We'll find the intersection points, the regions where the graph is concave up and down, and we'll find the regions where the graph is increasing or decreasing. So let's start with example number E. So this is example number E because A, B, C, and D were done in the two other previous videos. Okay, so in E, our function is x to the power of 4 minus 4x cubed minus 5. Okay, as before, we're going to start by finding the first and the second order derivatives. So the first order derivative is going to be 4x cubed minus 12x squared. Second order derivative is going to be 12x squared minus 24x. And then in part 1, the stationary points we find by taking the first order derivative, equating it to 0, and then solving. So we're going to have 4x cubed minus 12x squared equal to 0. Then 4x squared is a common factor here, so we're going to have x minus 3. So this is telling us that we're going to have two stationary points, one at x equal to 0 and the other one at x equal to 3. Then we analyze each of those. So at x equals to 0, the first thing we need to find is the y-intercept, is the y-coordinate, and in this case simply going to be the constant term here. So that means our stationary point coincides with the y-intercept. Then for the nature, we need to use the second order derivative to see whether it's concave up or concave down. However, in this case, if we plug in x equals to 0 here, we're going to get 0 minus 0. So this implies that the second derivative test is inconclusive. And so when the second order derivative test is inconclusive, we revert back to the first order derivative. So we're going to have to use y prime to determine what the nature of this stationary point is. So the idea is, so our stationary point is at 0. So we know that at 0, the gradient is horizontal. So we need to determine the gradient on the left-hand side of x equals to 0, the right-hand side of x equals to 0. There are 4 possibilities. It could look like this. It could look like that. Could look like this, and it could look like that. Okay, so and this is our stationary point here. So if we start on the left hand side, I'm just going to choose a point -1. So we need to find the first order derivative at -1. So if you take this and plug it in the first order derivative, which is this function here, So we're going to have 4 times -1 cubed, which is -1. Then we're going to have 12 times -1 squared. So this is going to be 4 minus 12 minus 16. Okay, if the first order derivative is negative, means the function is downsloping. It's got negative slope. So what this is telling us is that on the left hand side of x equals to 0, function is looking something like that, like a backslash. And then if we take a point on the right hand side, x equals to 1, so we're going to do x equals to 1. It's going to be like immediately to the right. We know there is another stationary point at 3. Okay, so we don't want to go beyond 3. So if this is 1, this is 2, we know there is another stationary point at 3. So we want to choose a point somewhere here. So we're going to use x equals to 1. So when we plug in 1, it's going to give us 4 minus 12 minus 8. This is telling us that the function is still downsloping on the right hand side of 0. So if the graph is like that there, so this is telling us that x equals to 0 is an inflection point. So 0, -4 is an inflection point. So notice that we can only conclude this way after doing the analysis. Just the fact that the second order derivative is 0 is not enough to suggest that it is an inflection point. It is possible for the second order derivative to be 0, and yet the point at hand is not an inflection point. Just for the sake of interest, if you analyze this function here, and in particular the point x equals to 0, you will find that at this point the second order derivative is 0, but x equals to 0 is not an inflection point. All right, then let's go to the other point, stationary point, which is 3. So when x equals to 3, we find that y is -31. And then the second order derivative, which is going to give us concavity, that's going to be 12 times 3 squared minus 24 times 3. This gives us 36. So this is positive, and it's telling us that at x equals to 3, function is concave up. So this implies that 3 -31 is a local minimum. Okay, so, and of course the this is 0 minus 4, 0 minus 5. This is 0 minus 5, the other stationary point, which coincides with the y-intercept. So 0 minus 5 here. So with this information, we can now make a sketch of the graph. So the graph is going to look something like as follows. So at 0 minus 5, we have got a point that looks like this. Then at 3 -31, we've got a point that looks something like this. So this suggests that we can join these two, and our curve is going to look something like that. And indeed, that is what the graph of this is going to look like. So something like that. Okay, So that's going to be the shape of our curve. So this point is 3, negative 31. This is a 0, negative 5. Okay, now so let's turn into the inflection points. From this, it suggests that there should be 2 inflection points, because this side, the graph looks concave up, this is concave down, so that's one inflection point which we've already found, concave down here, and then the rest of this is concave up. So that means we expect another inflection point between 0 and 3. So let's see what we get if we take the second order derivative and equate it to 0. So second order derivative is 12x squared minus 24x. Then 12x is common here. So this is telling us that there is an inflection point at 0 and there's another one at 2. The one at 0 we have already determined through the analysis of part 1. So it's just the one at x equals to 2 that we need to focus on now. So when y equals to 2, we're going to have 2 to the power 4 minus 4 times 2 cubed minus 5. This gives us negative 21. So 2 negative 21 is an inflection point. And then the issue of concavity can now be discussed. So that means somewhere around here we have got the inflection point to negative 21. So on the right hand side of this point, the graph is concave up, and then on the left hand side of 0, graph is concave up as well. So we're going to say concave up over, so on the left hand side of 0 is given by this, and then on the right hand side of 2 is given by that. And then the graph is going to be concave down over, so that's just going to be between 0 and 2. So only this segment of the graph is concave up, so over this interval here. Then regions of increase and decrease, again from the graph. On the left hand side of 0 decreasing, right hand side of 0 still decreasing up to x equals to 3. So decreasing over this region, union this region here, and then the graph is increasing on the right hand side of 3. So x is bigger than 3. All right, so that is about that in terms of analyzing and sketching this curve here using calculus. What we're going to do now is we're going to give you a chance to do a similar analysis for this curve here. Y equals 11 plus 8x squared minus x to the power 14. So if you'd like to pause the video and then work through this one, and then when you continue the video, you can compare with our analysis. Okay, we now scroll down to our solution of part F. So we're going to start by finding the two derivatives, the first order and the second order. Then we find the stationary points by equating the first order to 0 and solving. We get 3 stationary points, 0 plus 2 and minus 2. When x is 0, y is 11, which coincides with the y-intercept. Then again, when x is 0, the second order derivative is going to be 16. So since this is positive, it tells us that the concavity is upwards. So 0, 11 is going to be a local minimum. Then when x is 2, y is 27. The second order derivative is negative, which implies concave down, which corresponds with negative. So 227 is a local maximum. The values for negative 2 are identical as the values for 2. So we've got another local maximum there. This is because our function is an even function. You can see got only even powers of x here. So our function is an even function. So the graph we expect it to be symmetric about the vertical axis. So with these 3 pieces of information, we can now piece together our graph. At 0, 12, we have got a local minimum. Sorry, 0, 0, 11. So at this point, it looks something like this. At 227, we've got a local maximum. So graph looks something like that. Negative 227, we've got another local maximum. So graph looks like that. Okay. These turning points suggest that the graph will take this general shape. And indeed, of course, that is what the shape of this graph is going to be like. So this is going to be 227, negative 227. This one here is 0, 11. All right. So in terms of concavity, we can see that it's concave down up to about here, then concave up to about there, and concave down. So we expect 2 inflection points, one around there and another around there, and of course we expect them to be symmetrically placed. So if we set the second order derivative to 0 and solve, so there's our second order derivative, implies x squared is 4 on 3. So x is 2 on root 3 plus or minus. If we plug these into the y equation, both of them are going to give us 179 over 9. So that means this point here is 2 over root 3, 179 over 9. This one here is negative 2 over root 3, 179 over 9. And so between these 2 points, between 2 root 3 and between negative 2 over root 3 and 2 over root 3, the graph is concave up, as we can see. And then outside this range, so we could write this for magnitude of x bigger than 2 over root 3, the graph is concave down. Okay, then in terms of ranges of increase and decrease, those ones are divided by the points of by the stationary points. So on the left hand side of negative 2, which is here, graph is increasing between 0 and 2. The graph is increasing, so we can say the graph is increasing over x is less than 2 union between 0 and 2, and then the graph is decreasing over, so that is going to be between -2 and 0, and then on the right hand side of 2, so x bigger than 2. Alright, so it brings us to the end of this video. Thank you for watching. Please do subscribe. Do not forget to subscribe and like the video, and we hope that it has been very helpful to you. Thank you.